This presentation is about heat, or more precisely the measurement of heat and how it relates to chemical reactions. The science of measuring heat is called calorimetry, where calor actually means heat and metry just means measurement. The equation that I like to use for this, and I think our book uses this as well, is that heat is equal to SH, which stands for the specific heat. Most of the time this is going to be water. M is going to be the mass of the water, and delta T is going to be the temperature change that we observe in the water. So almost all the time these terms refer to the water, but you have to be careful. Sometimes we're talking about something else like a metal gaining heat or increasing in temperature. So we have to be careful and relate the temperature change and specific heat and the mass. They all have to be for the same substance. So you have to be really careful because a lot of the problems that you'll see have several specific heats mentioned, several masses, several temperatures, and it's kind of tricky to keep this all straight. I usually try to be a little more straightforward, but books sometimes are not as straightforward. I always refer to the equation, the heat equation here, as the Schmidt equation. So SH, the sh sound, M and T. So the Schmidt equation. So like I said, this SH stands for specific heat. If we're dealing with water, the standard specific heat of water is 1 calorie per gram degree Celsius, or 4.18 joules per gram degree Celsius. And this basically tells us the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. The mass, as I said, is the mass of the substance, and usually this is the stuff that you have your thermometer stuck into. And the temperature change is always the final minus the initial. So we are always using our final condition and subtracting the initial condition in science. So here's a problem. I've got a calorimeter. It contains 225 grams of water at 20 degrees Celsius, and we've done something to it to cause its temperature to increase to 31.2 degrees Celsius. That could be pouring in a warm water sample, or maybe dropping a hot chunk of metal in there. Or this could even be caused by a chemical reaction, like an acid and a base reacting with one another. So we want to know what amount of heat was gained by the water. So this is not something that we're going to use factor label for. We're going to use a formula, and it's our old friend, the Schmidt equation. So what I know here is that I have the Schmidt equation, and the specific heat of water is something that's necessary. The mass of the water is given, and the temperature change, or a means of calculating the temperature change, is given. So the final temperature is 31.2 degrees Celsius. The initial temperature was 20, so if I just do a simple subtraction, I find that the temperature increased by 11.2 degrees Celsius. Or you might notice that I've got Celsius degrees here. Grammatically, if we take a difference, and we're talking about a difference, then we're talking about Celsius degrees. Okay, so when I plug all of this into the equation, all of the units will cancel. If you notice, the grams and degrees Celsius are in the denominator part of the specific heat, and then I've got grams of water and Celsius degrees for my temperature change, and those will cancel out. And the only unit that's left is calories, and when I do this, I get 2,520 calories. 2,520 calories was gained by the water. So from the water's perspective, it's undergoing an endothermic process. It's gaining heat. Okay, so my next thing to ponder here is the water gained 2,520 calories, and this was caused by dropping a chunk of hot iron into the water. So how much heat was lost by the iron? If you remember our old friend, the first law of thermodynamics, or the concept of conservation of energy, energy can't be created or destroyed is the old middle school definition. Or we could say that the energy of an isolated system is constant, so any heat that was gained by the water had to be lost by something else in the system, and the only thing in our simple system is the iron, so the iron must have been what lost the heat. So the iron lost 2,520 calories of heat. If I push this a little bit further and I look at the specific heat of iron, which is tabulated in our text, there's a table in chapter 2 for a variety of common substances like iron and aluminum and a few others. And it gives their specific heats. And the specific heat of iron is 0.108 calories per gram degree Celsius. So it doesn't take as much heat energy to change iron by a degree Celsius as it does for water. Water's is 1 calorie. So it takes about 1/10 the amount of energy to increase iron by a degree Celsius. Iron has an unusual, or not iron, but water has an unusually large capacity for gaining heat. Okay, so we want to know what was the mass of the iron in the sample. So I know the heat equation, the specific heat equation, and I know the specific heat of iron. I don't know the mass of iron. I know the initial temperature of the iron, but I don't know the final temperature of the iron. And I have to throw in one more law of thermodynamics, and oftentimes this is referred to as the zeroth law of thermodynamics, sometimes called the law of thermal equilibrium. And it basically states that when any two objects or substances are placed in contact with one another, they're going to reach thermal equilibrium, or in other words, the same temperature. So therefore, if the water reached a final temperature of 31.2 degrees Celsius, then so did the iron that was dropped into it. So now I know the temperature change. So it was 68.8 degrees Celsius. Final minus initial, technically it's a minus sign, but we're really only going to work with magnitudes here, and then kind of do our finger pointing to decide whether heat was lost or gained. So I'm going with a magnitude of 68.8 degrees Celsius change, and if I plug that into my Schmidt equation, I know the heat that was lost by the metal. It was 2,520 calories. I know the specific heat of the metal. I don't know the mass, and I know the temperature. So if I rearrange this equation by dividing both sides by 0.108 calories per gram degree Celsius and 68.8 Celsius degrees, then the mass will be left all alone. So if I divide all of this out, so basically the 2,520 divided by 0.108 and 68, I'm going to be left with the mass. And the mass of this sample is 339 grams. So I dropped a large chunk of iron into that small amount of water. Remember I said that water has a much higher specific heat, so it takes a lot more energy to cause the same temperature change in water. Okay, we can also look at the calorimetry with respect to food items, and I think we'll do a lab this semester where we'll try to measure the calorie content of food using a simple pop can calorimeter. But anyways, the standards accepted quite widely for the energy content of the major components of food, fat, protein, and carbohydrate are given here. So 9 calories per gram of fat, 4 calories per gram for protein, and 4 calories per gram for carbohydrates. And if you really think about it, and I tipped this slide sideways for some reason here, but anyways, these are conversion factors. Anytime I've got two different units stacked on one another, then what I have is a conversion factor. So these allow me to go back and forth between calories, big calories, kilocalories, and grams of that substance. So if I know the distribution of fats, proteins, and carbohydrates in a food sample, in this case 10 grams of fat, 15 grams of protein, and 30 grams of carbohydrate, I can find out what the total calorie content of this food is. So all of those Fat, protein, and carbohydrate grams are starting points. And then I can use the calories per gram to convert each of those into the total calories offered by those quantities of fat, protein, and carbs. So if I plug those in and then multiply through the top, divide by the bottom here, I get 90 calories contribution from the fat, 60 calories contribution from the protein, and 120 calories contribution from the carbs for a grand total of 270 big food calories, not science calories. That would be 270,000 food calories, or sorry, 270,000 science calories.